This is the example on slide 84 of our Chapter 19 PowerPoint, and the question states to use the tabulated free energies of formation to calculate the equilibrium constant for the reaction at 298 K. And then it states the reaction and gives us free energies of formation of the reactant end product. So in order to relate delta G and the equilibrium constant, we learned a new equation on some previous slides, which basically states that the standard free energy change of a reaction was equal to a negative R, just the gas constant, times T ln of K. R is going to be, once again, in units of it's 8.31 joules over mole Kelvin, and our T is going to continue to be in Kelvin, and then K, of course, is unitless. But in order for it to be unitless, we have to make sure we have the correct R and T so that all of our units can cancel out. So this problem, we're going to be using tabulated delta G values to calculate delta G. We know what R is, it's the gas constant. It states that our reaction is taking place at 298 Kelvin, so that's our T, and we're going to plug all of these values into the highlighted equation to solve for our unitless K. So first thing I'm going to do is figure out my delta G naught of reaction using the sum of the products minus the sum of the reactants. So that's going to be equal to 2, because I have 2 moles of products, times 51.3 minus just 99.8. So when I multiply the 2 times 51 minus 99.8, I should get 2.8 kilojoules, and it's technically kilojoules per mole. And if you want to convert that to joules, because we're going to need to plug it into the equation, it's going to be 2,800 joules per mole. I just moved the decimal over 3 spots. So that's my delta G naught. My R is still 8.314 joules over moles times Kelvin, and my T is 298, which is stated in the problem. So first thing we're going to do before we plug in the numbers, I'm going to rearrange and try and get K a little bit more by itself. So I'm going to divide ln of K on this side, divide by ln of K on that side. Actually, strike that. I don't know what I was thinking, because I really don't want ln of K in the denominator. I'm going to divide by negative RT, both sides. There we go. So then I get ln of K is equal to negative delta G, excuse me, over RT. So now ln of K, our delta G naught is that 2,800 joules per mole. R is 8.314 joules, joules over mole Kelvin, and our T is 298K. So if we multiply, divide, all that, our moles cancel, Kelvin cancels, and joules cancel, which is good because we want our K to be unitless. So then I get that ln of K is equal to negative 1.13. And to get rid of a natural log, we're going to raise it to the e. E raised to the power of ln is going to get rid of our natural log, and we're going to have to do the same for the negative 1.13. So in your calculators, it should be e raised to the power of negative 1.13, which is going to get rid of our ln of k, or just our ln, not k, and that's going to leave k equal to 0.32. And that is your final answer.